last talk of the season. My name is Janet Callahan. I'm Dean of the College of Engineering here at Michigan Technological University. And so Husky Bites is a free webinar, as you know, and our location up here is in the Upper Peninsula of Michigan, where we have 301.5 inches of snowfall at the US 41 road gauge, according to a reading from Ralph Larson today. So thank you, Ralph, and you'll have to give us an update next week because I think we're due for another 20 inches or so. I mean, who knows what, but a blizzard is coming in on Wednesday. So I'm going to share a screen and show a couple slides, and then I'm going to introduce the speakers. So once again, welcome. This evening's talk is sponsored by the Department of Mechanical Engineering, Engineering Mechanics. As I said, this is a free webinar. We encourage you to invite your friends, your neighbors, prospective Michigan Tech students. It's a family-friendly event, and we hold it on purpose, kind of during dinner hour, hoping that people will watch us while they're eating their meal, hence the bites. So I wanted to just tell you what we were doing this weekend here at Michigan Tech. This is a glimpse of some of the people. These are the engineers who joined us for Michigan Tech's preview day, which was held Saturday, just most recently. So this is the engineering welcome. We're talking about some of the sustainable development goals that engineers aim to do. We had close to a record turnout, and I met a few Husky Bitesers who came up to me. And so one of them's from, oh gosh, I can't see their names, but for anonymity, I will skip their names. One is from Michigan, majoring in mechanical engineering on the upper left. And then the other is from Wisconsin, majoring in electrical engineering. And so these will be here at Michigan Tech this fall. And it was awfully nice to meet them. And you know, it's they came up to me and said hello because they recognized me. So I was very honored for that they said hello to me. So as I said, this is our next to last Husky Bites. And so our very last one of the season will have taken place right after another blizzard, but we'll be talking about some of the summer insects we see up here in the Keweenaw, and specifically some butterflies, moths, and fruit flies. And so Tom Werner is just a terrific speaker, and the co-host will be his former grad student Tessa Steenwinkel, who you will learn has a fruit fly named after her because she discovered it. So with that, I'm going to, I think that was my last slide. I'm going to stop sharing, and then I'm going to introduce our speakers this evening. So first of all, mechanical engineering mechanics faculty member, Dr. Fernando Ponta is on the left. He is the Richard and Elizabeth Hennis Professor of Wind Energy, and wind has been the theme across his whole life. And whether he's sailing in the wind or whether he's skiing in the snow, which is another way of harnessing energy with a shaped blade, he has made wind his passion across his career. He was born in Buenos Aires, Argentina, where he earned his PhD. He came to Michigan Tech after doing a postdoc, I believe at University of Illinois, Urbana-Champaign in 2007. And he's been here ever since because he loves Michigan Tech. He loves our water, our waves, and our wind. And we'll learn more about him during the talk. I guess I should mention his research is focused on computational and theoretical fluid dynamics, and especially as it pertains to wind. And so on the right, I'd like to also introduce our PhD student, Apurva Baruah, and Dr. Ponta has been his PhD advisor since 2017. Apurva is pretty famous here at Michigan Tech. He was the president for 2 years of the Graduate Student Council, where he was not only elected, but re-elected. And he has a bunch of hobbies as well. Apurva was born and raised in Mumbai, India, and apparently his mother watches our Husky Cam feeds. And if you're on right now, hi, Mom. So among other hobbies, he is the range safety officer for Michigan Tech's competition rifle team. So Apurva is very talented. I have this vision of him winning the Olympics skiing and with a rifle at some point in the future. So with that, these are two. This is the leader and a member of Michigan Tech's Wind Warriors team, and I'm going to turn it over to you guys to take it from here.
So we are sharing now our. So can everybody see the beautiful photo of this okay, great, offshore wind farm. So as you could see, this is the title of our presentation, The Wind Beneath My Wings, Sails and Turbines, So, but before we start, we are going to ask the audience a question, So, which, in your opinion, is the oldest documented use of a wind turbine? Documented.
And so there's four choices: around 300 BC, around 600 AD, around 1100 AD, or around 1400 AD. Interesting.
Wow, interesting. Very dynamic, the evolution of these statistics.
There you go.
Yeah, 79%.
Yeah, well, the audience is tending toward, in order, A is the most popular, B is the second most popular, and C, and then very few people think it happened in 1400 AD.
14 AD, yeah.
Okay. So what's the answer?
The answer is B. So, and that leads to the next transparency. So the first documented, let's say, application of wind power to generate, or to any task, is the so-called Persian windmill, or also called the Sistan windmill, which is, well, is related with the name of the region. Now it's present-day Iran, Is this photo that we could see here, where we have this construction made of essentially bricks, The lower parts that we could see here, all these chambers, are essentially where the mechanisms of the mill are located. They were mostly used to mill grain, and actually the wind collectors, or if you want, the converters, are these pieces of wood that we could see here, So they are a very simple and sturdy type of machines, Also the first real, again, documented application of wind power. They are also surrounded by these walls, these brick walls that provide shielding in order to make the machine operational. For the reasons that we are going to discuss in a second when we go into this scheme over here. So as I said before, I mean, they are so useful that, some of them are still, in use today, very sturdy, very easy to, make and build, and maintain. They are mostly what, or maybe actually the outmost example of the so-called, drag-driven or drag-based machines. What do we mean by that? That's essentially the primarily forces that push those, blades, if you want to call them. Actually, they are wooden planks, in order to produce power on the main shaft. Are essentially, those forces are collinear with the incoming flow, the one that impinges, like you will see here symbolically, onto those wooden planks. Well, more properly, and this is how I say it in my wind energy class, this should be called a differential drag machine. So as one half of the rotor is shielded, what we have is that all these forces operate in one side of the central axis, which, by the way, in this case is vertical. It doesn't need to be, for drag-driven machine, but typically, drag-driven machines are vertical axis. So that generates this, leverage or moment, if you want, or torque, that makes the machine rotate. One of the typical things that happens with drag-driven machines is that they're incredibly inefficient. Drag creates, which, by the way, is the essential mechanism, as I said before, in the way that the blade interacts with the wind. That creates a lot of frictional effects, either by turbulence, by viscous friction, a combination of both, if you want. And that friction ultimately is energy that comes from the flow, but ends up as heat. So essentially it just goes, far away downwind and essentially ends up engrossing the entropy of the universe. It's subtracted from the wind, but it doesn't convert or doesn't translate into useful mechanical power on the shaft. So after several centuries, and here there is a bit more of uncertainty on when the so-called Dutch or European or a four-post windmill, which is depicted in this photo over here, for obvious reasons, it has four, wooden posts, appears. Even though the actual documented record is around the 12th century, essentially the 1100s, nevertheless, there is some sort of anecdotic evidence, that those machines could have been around for a longer period, in some places in Europe. These machines are based, in a different physical mechanism. Actually, any flow is going to produce these two, forces, any flow acting on a solid surface, lift and drag. The question is that in the case of this Dutch windmill, the primarily force that is used in order to produce the driving torque that moves the machine is the lift force. Here we have some sort of very schematic depiction in what we may call, a modern airfoil shape, where we could see that, well, the resultant incoming velocity over here, is going to produce a force which, well, again, drag is going to exist here, and it's going to produce a force, collinear with the incoming flow, but the lift force acts in the normal direction to the incoming flow. Lift has several advantages in terms of a mechanism for exchange of, power, with an incoming flow from a solid, let's say, part, is because it could be produced, with very little friction involved. Actually, lift per se doesn't need friction to be produced as drag, So, moreover, for a well-designed airfoil profile like the one that we have seen here in this example, you can produce a huge amount of lift with just a minimum amount of drag. So to the point that for highly advanced, thin airfoils used in aeronautics, that proportion could go in more than 100 to 1. So essentially, if we had to depict, the drag force produced here is going to be a teeny tiny, dash over here compared with this huge lift force. And in ideal conditions, some airfoil profiles could go beyond that, more than 100 times in their lift to drag ratio. So essentially, you need a small surface to produce a lot of force, exchange a lot of momentum and energy with the incoming flow, and produce very little friction. So essentially, it's going to be a mechanism, any machine, based on the lift force as the primarily driving, factor in the production of power, is going to be extremely efficient. So this is not trivial, because in the case of a wind rotor, this translates into a dramatically higher efficiency of the conversion process between the kinetic energy that is available on the flow and the power, mechanical power produced on the shaft. So curiously, and this is why, we have been talking so much about sailing, the evolution that led along these 5 or 6 centuries, between the typical drag-driven machine to the lift-driven machine goes in parallel to the evolution of sailing rigs that went from square, sailing rigs into the more modern, mostly triangular sailing rigs. And again, the old sailing rigs were based in drag. The modern, sailing rigs are mostly based, and say mostly because they can use drag too, but they are mostly, reliant on lift forces. Moreover, if you look at the blades of the Dutch windmill, this is a more modern photo, but it reflects what we are going to have, in the, what they have, the Renaissance, let's say, so we're going to have these posts, providing, structural integrity, some, grid of wood here that provides some support, but the actual surfaces that, or aerodynamic surfaces, if you want, that exchange, those forces, capturing or harnessing the energy of the wind, are these pieces of canvas that you see here, that they look like sails, they are sails, So, but, well, before going, into that analogy that we're going to go in a couple of minutes, one thing that I would like to emphasize is that this evolution, that took place in this, 5 or 6 centuries over here, was fundamental in the evolution of the wind power as we know it today, because essentially this machine, or the basic principles from the physical point of view of the Dutch windmill that we have seen in the late Middle Ages, is essentially the same physical principle on which the current high-tech, wind turbines so today operate. They are more sophisticated, they have been more refined, but physically they are exactly the same type of axial horizontal wind turbines. But before we go into this analogy with the evolution of sailing rigs, let's go into some question, another poll question. Which do you think is the largest application of wind energy in terms of total accumulated terajoules along history? First option, water pumping. Second option, flour milling. Third option, sailing. And fourth, electricity generation. Again, a lot of competition. Look at that. So,
That's a good one.
Yeah.
You'd have to make a lot of assumptions about all these things, but
yeah. One thing that pay attention to what we said here, total accumulated terajoules. We are talking about the the amount of energy, not the individual application, not how many turbines you have here and there, etc. Yeah.
I'm going to go with sailing as well. I think we've got two popular answers here, water pumping and sailing.
Yeah, you are the winner. Sailing is by far, and then I'm going to leave Apurva to explain this,
So all those who chose sailing, if we consider, there's no way we can kind of quantify the amount of energy that was used by sailors since the beginning when they start sailing, when they explored around the world. But considering all of that, the use of wind power for transportation through vessels, by far, even though we might not have concrete numbers, it kind of eclipses any other use of wind power that mankind must have involved itself in.
A long history. Yeah. So yeah.
So when we talk about the evolution of sailboat rigs, we need to understand a little bit about the points of sailing, as in how a sailboat moves with wind. And there are, for simplicity purposes right now, we're going to talk about three primary modes of sailboat or points of sails. The first one is very simple, the wind coming from our back, which is we are sailing downwind, and the drag forces, the drag forces in the downwind is the most dominant force. And that's why we can go and we can sail with the wind. The other next type of point of sailing is when the wind is from the side, whether it is exactly from a beam or the wind is hitting us on the beam of the boat or at an angle, but primarily from behind. In such a situation, we do have a lot of lift as well and drag, but it is primarily more of lift. The third point of sailing is when we are heading much more towards the wind. We can never sail exactly into the wind, but we are still sailing upwind. In this point of sailing is when the forces that are acting on the sailboat or the sail, they are primarily dominant and full of lift. And it is the lift forces which allow us to sail close to the wind, which is what allows us to sail upwind. Now, the differences in the drag dominant versus lift dominant sailing was evident in the rigs that were developed. So back in the day, especially if we take the example of the Vikings or some of the frigates even of the Middle Ages, they were drag dominant sailboats which had square rigs. They could primarily go downwind. They could go a bit off the wind as well if you could angle your rectangular, if you could rotate the mast and angle your rectangular sails a bit. But again, they were limited to not being by not going too much into the wind. With passage of time, we started developing sails which were more triangular, which we started to understand the effect of the lift forces, and that led us to the development of the clippers and especially the boats that we see nowadays, which are called the Bermuda rigs, which have triangular sails, and what propels the boat is primarily lift. that actually gives the boat to go upwind and not just be limited by sailing with the wind. What you see here is Dr. Ponta's boat, the Avanti Bianca, and we're actually racing in the Portage Lake here. And I'm actually between the two Pontas. The one in front is Vicky, and then behind is Dr. Ponta. And this is a race that happens in Portage Lake over the summer. So that is something that we were talking about. We're really excited about the summer to get in.
Yeah. Oh, so one thing Janet was asking before, which type of sails are, there. Actually, you can see 3 sails, only 2 of them are deployed, So the main is the one that Apurva, is showing now. In the front, we have that reaching spinnakers, which we call the poly, because it's made of polyester, So, and then the other one, which is the jib, at this point is not in use, is this roll thing, that tube in dark color. It's a carbon fiber, kind of sophisticated material science, Anyway, sail, which is rolled in now because it's not necessary on that particular point of sailing. One thing that we can add is that when you are in this type of, this is mostly a ridge, a ridge dominant, point of sailing, the one in the middle of that kind of scheme that we have above, where you may have a combination of drag and lift operating together, lift is usually, especially with this type of rig, the most important one, but you can in a modern boat, sail by drag, so when you essentially deploy open completely, trim off your sails and you go dead downwind, but essentially the big difference is that with modern boats, you can, pull the sails in and activate that, mostly lift or lift dominant mode of sailing that allows you to go, well, faster and in general, and also closer onto the wind. That thing have, well, I mean, I don't want to spend too much,
I know.
Yeah.
All right, we're going to have to move it along.
Yes.
Fernando, we're already at 6:17.
Wow. Okay. So, well, when we say that this inherent efficiency of the lift generation process, versus the generation of drag, and all these associational frictional losses is essentially the physical underpinning, of the fundamental progress in wind power. In modern times, we can trace some sort of similar evolution in essentially that refinement that moves us from the Dutch windmill into the high-tech, propeller-like wind turbine of today, which is the incorporation of a lot of optimization in aerodynamic, surfaces and airfoil designs, etc. Material sciences too, but mostly aerodynamics that are used in aeronautics. So without entering too much on details, because obviously, well, we have these time limitations. But here, where we can see is some sort of a schematic view of this classical, 3-bladed propeller type wind turbine of any size, and we can see here, so how we can decompose, if you want, the typical blade into segments. Later, we're going to return a bit to this notion of the blade segments. Each segment is some sort of slice that you can cut, there, and it's going to have some sort of, and I say some sort of airfoil profile because it may vary, along the blade in different shapes, which are more suitable to, operate regions closer to the hub or closer to the tip, etc. But well, here the idea is that the lift that, if you remember that previous picture we have shown, which in this case is going to point, more or less like this, in this direction, is going to have a big projection of force, into the direction normal to the chord, of the blade, the chord of the airfoil sections, which is going to be discharged just, as a structural force onto the blade itself, just bending it. But there is going to be a proportion, or at least a projection of that lift force that is going to point ahead towards the leading edge, and that's the one that is going to push, well, this blade segment and all the blade segments along the span and the blade segments of each one of the blades to create the driving torque that keeps the machine running. Again, this is with the the incorporation of this advancements, of the aeronautics in the last 100 years, is how we arrive to the highly I would say, efficient and specialized machines, that we have today. Machines have been increasing in size dramatically. Here we have, just as an example, the photo of the RE Power 5 megawatt is a machine that has a rotor diameter of 126 meters. So later we're going to ask another question. So just to give an idea of how big these machines are, this prototype was tested in 2001. So it's essentially, we're talking about something that really exists, today. So the nacelle of this machine has the size of a bus. And this small, blue spots that we see here, if we zoom in, are actually people walking on top of the nacelle. And that, leads us to which is the effect that this, I would say efficiency or improvements in terms of the economics of wind power have been correlated with improvements in technology. I love this plot because even though, it goes some years back, it shows some sort of, I would say as a test case, what happened in Europe, which were in general, the European community, or the European Union now, was one of the first economic groups to really go into wind power. And we could see that in the last, 15 years, how, wind power has been growing systematically, beating first, overtaking, if you want, oil as the fifth largest form of electricity generation, then nuclear, then hydro, then coal. And, even though we don't have a recent data, because the pandemic has distorted a bit the collection of data, in 2019, wind was very close, was posed, to overtake natural gas as the first and the most important source of electricity in the whole European community. We're talking about the big, economic group, which together with China and the United States is one of the biggest in the world. Now in 2022, probably, wind is already by far, the most important source of installed capacity in Europe. And this is not just a question of history, it's what we can expect in the future. So what we can see here is a projection, estimated by our National Renewable Energy Lab, which is part of the US Department of Energy, which essentially compares, the cost of the kilowatt hour, what is called the levelized cost, of the kilowatt hour, or in this case, the megawatt hour, comparing, basic important, sources of electricity, coal, nuclear, natural gas, utility scale solar, and onshore wind, As you could see, wind is already by far, especially compared with coal and nuclear, the cheapest way of generating electricity. Obviously, this is an average, so in some places could be cheaper than others, etc. But as an average, is the cheapest way of generating electricity. And it's not only today, it's the projections for the future, that they're expected, that advantage, essentially, economic advantage, is likely to increase and increase and increase systematically for the next 30 years, while the rest of the sources are likely to, remain constant, especially nuclear and coal, and natural gas actually is likely to go a bit up, because, well, obviously the depletion of gas reserves. So this evolution is not only just the technology, it's also, the increase in the size of the typical, machine, or the, essentially the state of the art, wind turbine of today. That leads to our third question, which is, in your opinion, the approximate diameter of the largest operational, no planned, operational wind turbine prototype of today? So do we have the,
can we have the poll?
Could we have the poll, please?
It's good people had a chance to think about that. And I'm trying to convert to like feet in my head and to the size of a stadium.
Yeah.
I'm just gonna guess bigger here.
Yeah.
220.
This could have been a tricky question, that
Yeah.
we put there, because there are two key words there. One is operational and the other prototype. So,
well, and the choices
yeah.
range from 80 meters to 220 meters.
Yes, exactly. So Later, Apurva is going to talk a bit more about how that compares in more practical, uh, how to translate into more practical distances. The actual answer is 220. Why?
Ah,
Because, we talk about which is the largest operational prototype, a prototype that this running is tested, the largest one. Most of the people answer 160, which is not so wrong when you talk about which is the largest operational commercial turbine of today. Because if we talk about the size, well, actually between 120 and 160, they form the core of the turbines that are installed today commercially. But the state of the art, the cutting edge in terms of size of turbines is 220. And there is a reason for this continuous scaling of if you can go to the next transparency. Yeah. So here. So this plot, has it's essentially a depiction of I like it because it depicts the levelized cost, the evolution of the levelized cost of energy, wind energy from the beginnings of the modern wind power era in the 80s, mid 80s, early 90s, all the way, to 2013, which was at the time where this information was collected. Again, with the pandemic, there had been some delay. I would have been expected in 2020 a new, an update version of this plot, because you need some years of operation in order to have a decent sample of statistics in terms of estimation of the costs. But there is something which is very, very clear here, is that this rapid and dramatic decay, that we have in the levelized cost of energy, as you could see, that is very, very important, is correlated directly with the systematic increase on the size of the individual machine. And this is a tendency that is likely to continue. And that's the reason why, those companies spend so much money in creating these huge prototypes, because there is a question of economics of scale. Again, there are a lot of things in material sciences, power electronics, aerodynamics, you name it, that can contribute to this improvement in the cost of the wind power, or the individual cost of the levelized cost of energy. But, the upscaling is a fundamental factor. When is it going to end? We don't know. Actually, we can have some speculations. We can discuss later if people is interested in the question section. Where are we at today?
So anyone who got 220 meters, rejoice, you were correct. That is 220 meters is the largest currently installed diameter of a turbine. This is the GE machine. They're currently testing it in Amsterdam, in Netherlands. This is a machine that is also going to be installed in a project closer home in the United States. It's just off the coast of Massachusetts. People have heard of Martha's Vineyard. That is where they're going to install this. And that is an offshore wind farm as well. Now, to put things in perspective, the turbine blades of this are 107 meters long, and that is a little less, just a little less than a football field, American football field, end to end. That is how long one blade is. Another way to think of this is it would take Usain Bolt, the fastest human on Earth, 10 seconds to run from one end to the other.
Yeah.
So that has been one of the big focuses in the area, is to improve and make individual turbines better through all these years. But moving forward, we need to think beyond just the scope of one turbine as well.
Mm-hmm. So, and the real thing here is that even though you can, extend or invest time and effort and resources, which is very valuable, in improving I would say, the performance of the individual turbine in many aspects, technological, economical, resilience, you name it, wind turbines don't operate alone. They operate in farms, and farms create a challenge. You can see here a couple of photos, which shows one inland, one offshore. This one is in Kansas. No? So as you could see that, it's not only just one row of turbines, of the old wind farms in the past that, experimental in California. Here we have, turbines distributed in depth. And essentially that creates, limitations in the way that turbines interact together. So essentially, they are what is called in the jargon creating, a shift in paradigm from, paying attention to the optimization of the individual turbine to go into the optimization of the operation of the whole farm. So it's interesting that there are many aspects on which turbines can interact in a farm. They can interact via the electric grid that interconnects them, but most of the interaction that occurs between turbines is via the flow field, and in particular, the wakes emanating from turbines that are upstream of the others, as we could see here in this offshore farm, are the main mechanism, in which one turbine can affect the other and vice versa. So, and this is where, even though we, our research group has spent 15 years working on optimizing many aspects of the simulation of individual turbines, now in this project with Sandia, we are shifting that paradigm, essentially following that shift of paradigm into the analysis of wakes. Well, I mean, wakes sometimes are visible and sometimes are not, So here we have in this offshore farm, the humidity of the ocean provides enough, vapor on the air that condensates into droplets and then makes visible, these wakes that we see here emanating, from the turbines, but they're always there. Even if we cannot see them, as in Kansas, because the air is mostly dry, So wakes are extremely complex to analyze because also they have the tendency to evolve after they are shed, and they can interact with the background wind, to create very complex structures that are difficult to predict where they go and how they, going to end up in their shape and pattern when they impinge on the turbines that are behind. So mostly wakes are made of vortices, and even though we cannot see individual vortices here, they are there. They are complicated patterns of vortex filaments. A vortex is essentially an eddy, like a mini tornado, if you want. And if you want to imagine how they interact, well, think about them as, a collection of spaghettis in a cooking pot, mixing around and, moving around. Well, that's the way that they interact. So in general, the most powerful vortices that we're going to see in any aerodynamic surface are emanating from the tip. Like, in this photo where, smoke tracers are utilized to depict the trajectory of the tip vortices on this, experimental, if you want, or test wind turbine, but they emanate all over the place. It's not only wind turbines that, generate those vortices. If we go, to wings, for example, all aerodynamic surfaces essentially produce them. And as I said before, wakes are made of vortices. So here we have an interesting photo. I love it, you also show it in my fluid dynamics class, because, well, it operates, essentially it shows, that airplane operating in what presumably could be a frosty morning, with the sunshine, in the back. And then you could see the tip vortices emanating from practically the tip of the, of the wings. And what we see here is the axis of the vortex, So essentially it's like, a tube that indicates just the core of the vortex, but the real pattern of velocities that are induced for these vortices, also courtesy of the humidity of the air, is what we see here, So essentially this rotational velocity pattern, around the axis of this, vortex tube. Here is also depicted in a more schematic manner, in this picture on the side. Well, I mean, this is not just a theoretical curiosity. In terms of aeronautics, for example, the action of these tip vortices are likely to produce substantial changes in the aerodynamic efficiency of the wings, to the point that, if you look modern airliners, even new versions of all, airplanes like the Airbus 320, etc. Now they have these winglets added in order to mitigate the influence of those tip vortices, which are likely to produce, those winglets, simple pieces of plastics, connected, to those tips. They can introduce savings in fuel consumption all the way from 5 to 10%, which is a lot. Not only wings, or wind turbine blades produce, as I mentioned before, vortices. Here we have a photo of the propeller on a World War II Hellcat, fighter. It's essentially trying to take off from the deck of a, of an aircraft carrier, where again, courtesy of the humidity of the air, we have this tracer, tracing the trajectory of the axis of these vortex filaments. Well, without entering too much on details, the tip vortices are the most important or the most visible because they essentially emanate from essentially the point where the distortions on the velocity field are the most intense because, the aerodynamic surface is ending. You have a solid on one side, you have air on the other, and then the difference in pressure induces this, swirling motion that then is advected downstream in what is called a trailing vortex. So, now we are going to enter into a very, 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 very quick and difficult to compress part of what we are doing now, and which is essentially the basic essence of the model that we are we have developed and we are employing today in our work with Sandia Labs. We call it the Gaussian core. Yeah.
I just want to say we already have 24 open questions. So if there's any, I know you have 20 more slides left. So if there's any chunks you can skip or go high speed through.
We are going to go high speed because we have groups of 5 or 3 or 4 that they are compressed together in like a mini movie. Tick, tick, tick.
Okay.
Anyway, so to make it brief, the mathematics is really complex, and obviously, as Jan said, we don't have the time, to go into the details. We are happy to, respond to questions later if people, is interested. But essentially, these vortex lattice techniques, what they do is just trying to simulate, the patterns, the velocity patterns on the wake by just analyzing and tracking the evolution of those filaments. Let's imagine that this is a segment of the blade, or one of those slices that we mentioned before. Is going to be characterized or is going to be associated or have, associated vortex filaments that are shed at the ends, the trailing filaments, each one of them, inducing this revisionary or rotating velocity pattern around, and then some other set of filaments which are called shed filaments that are emanating in, let's say, roughly parallel to that blade element. Let's say that we grab this blade element and we consider other element which is adjacent here and another one over here, and then another one in the other direction and another one on the other direction, and we can cover the whole span of the blade. So when we put this structure with the others, in the surroundings, what we're going to have is a network, and here is how it looks, in this kind of schematic representation of the wake, or the vortex wake, if you want, of this wind turbine. So here we can see this network is what we just mentioned before. The most powerful vortices are emanating from the tip and from the root, but there are others, emanated in the middle every time that you have some sort of change of the conditions, the shape of the airfoil, the tapering of the blade, etc. So here we can see a close, view of that. This network forms a lattice. Each blade emanates one of these lattices, and here we see, only for clarity, we are seeing only one, of the blades, or the lattice of one of the blades. But when we put the 3 of them together, we can create a long representation of the wake, as we have seen here. The plot that we are seeing here normalizes, indicates, a very typical, I would say, some sort of simple wake that we can create, when we put the model of this turbine in an imaginary wind tunnel with a constant stream, etc., and it creates this cylindrical shape. But when the, turbine is exposed to real wind conditions, like, for example, these ones that, Sandia has measured in their facility at Lubbock, Texas, we are going to have differences in velocity in the background wind, which is going to be slower at the bottom and faster, at the top. And that creates distortions in the pattern of vortices that are emanating. And then the vortices start to act up, by influencing each other, creating very complex patterns in which those spaghettis, if you want, those vertical filaments get together, and then start to create very difficult to predict trajectories and shapes for those wakes. So here we could see, it's like grabbing that same wake that we have seen before, cutting slices, progressive slices downstream, at 1 diameter, distant downstream from the turbine, 2 diameters. As we could see here, how the vortex stretches, splits, and in the end, we're going to have these concentrations of vorticity, which groups together many filaments, which join forces to produce very powerful vortex structures. As you could see, they have nothing to do, or it's difficult to connect the actual shape of the wake when it is downstream with the shape of the object that generated it, which is just a disk, So this, again, is not a theoretical curiosity, because each time that we have, or in each, say, conditions where we have these concentrations of vorticity are likely to produce velocity patterns that, well, essentially are going to hit the next turbine that is downstream. So,
and so what we see, or what we can measure, is how the wind is behaving, or what the flow of air is behind a turbine. And how that is done is in the Swift facility that Sandia has. It consists of 3 turbines, and on one turbine in the front, at the back of the turbine on the nacelle, they've mounted a laser. And what that laser does is it shoots a beam behind, and at specific distances behind the turbine, in this over here, we see that it's done this at 5 distances behind the turbine. It's able to measure the velocity at one point. Now, when it follows a pattern, which is called a rosette over here, once it measures the velocity at each of those points, with those data, we can get a map of the velocity at that particular spherical surface. Now, that forms the basis of how we validate our simulation results based on the lattice, the vortex lattice that we get. Because that vortex lattice is what results or induces the differences in the velocities. This picture that you see is what we have obtained from the result of the vortex lattice. If you see over here, a much more clearer picture is in this slide, where we're comparing the velocities at 2 specific distances behind the first turbine. One is 2 diameter lengths behind, and the second one on the right is 5 diameters. And if you see, we do see a very, very good agreement with what the real wind turbine measurements are. Now, what we are really interested in is these dark blue patches. Those are the patches where the velocity of the flow is very little or very less compared to the entire background flow. That is crucial in the design and the layout and the analysis of a wind farm. So the better we can predict and understand these regions, the better we can model farms and have a better production of energy.
Yeah. So now if we can see, and this is a very, very recent picture of the case that we just finished running and presented to Sandia. This case is still running, so we're going to continue having better, images later. But essentially, the picture may become even more critical, more difficult when we have more than one turbine in different, echelons, let's say, one behind the other. So as you could see here, the first turbine, generates a wake that, progressively intermingles with the second one to create a third, transition in those vertical structures. So now Apurva is going to, can you show the presence? As you could see, what we see here is the wake that essentially the trajectory of that the second turbine would have produced, it would have been operating alone. And suddenly with the wake that, because of the influence of the wake that emanates from the frontal turbine, that trajectory gets altered of those vortices. And essentially they start to merge together in such a manner that they create a different structure, which is completely new versus of what you can expect by analyzing only one turbine. These things are not trivial, as we mentioned before. For example, here we can see we selected just 2 variables to show which is the influence that, trying to analyze this impact of low velocity spots, or essentially variating or fluctuating velocity patterns. In red, what we could see here is the energy, or no, in this case, sorry, is the tip deflection, that you can see a long time, for the first turbine. And in black, is the one associated with the second turbine. When we start the simulation, let's say, imagine that we, can control nature and switch on, the shedding of vorticity. At the beginning, both turbines operate in the same manner. They have oscillations related with the mechanical operation, etc., flow pattern, but they are very predictable. Both of them receive clean air. But as soon as the wake from the first turbine impinges on the second one starts to depart. Not only it alters the average value of that displacement of the blade when it bends, but also it starts to oscillate dramatically in terms of the peaks, back and forth of that deformation. This is essentially not only a change on the operational conditions that also can create substantial fatigue accumulation that can compromise if it remains uncontrolled or unpredicted, it may compromise the operational life of the turbine to the point that the wind farm that is intended to operate for 30 years, it may end up being, have to be replaced in 5, which economically is a catastrophe. And something similar could be seen here in the production of power. It's not that obviously the production of power in the shaft is going to be more continuous, but it's going to be pulsations on the instantaneous, torque that is exerted on that shaft to the point that, well, I don't think that, this is going to be, in this case at least, so strong as to burn any, of the components in the nacelle, but it's going to create oscillations that can compromise the operational life. So essentially what we're seeing here is that, and understanding the wakes is fundamental to understand, very, very important, crucial aspects of the operation, of turbines that can have significant economic impacts and technical impacts. Just we are to close very briefly. There is a further step on which we are entering right now in our project with Sandia. It's essentially, here what we have is no more than a slice at, 2 diameters cut, cross section, 2 diameters downstream of the second turbine. As we can see how, is this process of absorption, if you want, or deflection of the second wake operates into the first one, and how, here we are seeing it, the second wake with and without the first one. And if we can put the first one, so essentially after the second wake got inside the first, the first get reabsorbed inside the second. So essentially what we have here is what in the jargon of vortex dynamics is called vortex merging or vortex coalescence. That means that vortices that were small, they merge together to create the bigger vortex tractor. The bad news about that is that bigger vortex tractors can survive longer, and they can travel farther downstream to impact, for example, the third or the fourth or the fifth row of turbines in the farm. The good piece of good news is that if you design a proper control strategy, what you could do is use the wake of the upper turbine to manipulate the wake of the downwind turbine in such a manner as in this one, to suck it up or to suck it to the side, essentially deflected in such a manner that you can force it, or at least herd it if you want, to avoid turbines which are behind, improving their operational production in terms of fatigue or even just, the power production. All that requires good modeling in terms of quality, of the wind farm, which is extremely expensive, something that you cannot conduct in a wind tunnel, because the differences in size between, a small, piece set farm that you can put in the test section of a wind tunnel is orders of magnitude with the kilometers that wind farm is going to occupy in reality. And this is what, is essentially the next stage of our collaboration with Sandia, with the people of controls, to use these models as a platform to test their control strategies to manipulate those wakes in the way that we want them to operate. And with that, I'm sorry about the extension. Thank you very much for your attention.
Awesome. Thank you so much. And folks, you can ask questions in the Q&A. And Apurva, you've probably already picked out a few questions to answer. And so just go ahead and read out the question, click on answer live, and then either one of you can answer the questions.
I'll go by the order in which we've received questions. One of the first questions that we've received is, why aren't there more sales on Dutch windmills? Which I'm kind of going to paraphrase as, why aren't there more number of blades in any turbines that you see these days? please let me know if I've paraphrased the questions wrong or I've understood the question wrong.
Well, they've got no way of answering, so you're just going to have to go
Okay.
with it.
Well, if we understand correctly, it's essentially asking why don't we have a higher number of blades? I think that in the Dutch windmill in particular, it could be related with simplicity of construction with the materials of the time. Essentially, you can have two long, posts. Actually, that's why they're called the four-post, windmill. So if we translate that into a modern conception, let's say a water pumping windmill with multiple blades versus a propeller type of, two or three blades, machines, is related with the speed at which the machine is going to operate in proportion with the speed of the wind. All this is measured by a non-dimensional quantity called the tip speed ratio. So it's something that is very difficult to explain because in the typical wind turbine wind power course that we teach here, it takes one class just to discuss that. So you can imagine that compressing that in a few seconds is complicated. But let's put it in this manner. It's not. There is one misconception, that sometimes they say, okay, let's put more blades in a machine and then we're going to extract more power. That's not true. The amount of power that you can extract, is relatively fixed, so essentially by the area, of the wind flow that you can capture and the efficiency of the machine. Essentially, the only thing that you could do by adding more blades in a rotor is essentially trading, of speed of rotation for torque. So essentially, a multiple blade rotor is going to rotate slower, but it's going to produce much more torque. But the product of the two are going to give practically the same amount of power. So essentially, the idea in the case of the water pumping windmill, that you have to very slowly turn one of those piston pumps, and you need a lot of force to do that. Well, it's an ideal piece of machinery. You can just connect it directly and it's going to turn very slowly, but with a lot of strength, a lot of force in order to pump that water. In a machine which is intended to drive an electrical generator at very high speeds in order to, connect to the grid, it's better to have the machine operating or extracting the energy via rotational speed, essentially light torques and big, high rotational speeds for the same. The same amount of power.
All right, and so Apurva, I would encourage you to kind of pick and choose questions because sometimes some of them you're not going to know the answer to.
Yeah.
So next question is, will knowing the accurate profile of the wake help with deciding the design of turbines depending on where they're located on the wind farm?
So
I'll repeat that again.
Will
knowing the accurate profile of the wake help in deciding the design of the turbines depending on where they're located on the wind farm?
Well, that's something that has been discussed, So in any case, most of the farms today, they have either they are composed either of the same machine, or variations of the same machine, But there have been discussions in the past of, for example, interspersing, vertical axis wind turbines in order to manipulate the wakes, increase mixing of momentum, etc., in order to reinforce or revitalize, the flow after going through the first row of turbines. That's a very interesting thing. Moreover, you can do that even without changing the type of machine. They have been talk about making, I'm not sure if with the camera you could see counter-rotating turbines side by side, because in that manner you can create, promote this exchange or vertical currents that can create a change of momentum between the upper layers, of the atmospheric boundary layer and the lower layers, so essentially enriching, grabbing energy, kinetic energy and momentum from the upper levels, and dragging it back, essentially promoting mixing and revitalizing the flow. So it is possible, yes.
Right, there's so many questions. We're going to have to answer them faster. Can the wake actually come back in reverse? This is a question for Apurva. Can the wake come back in reverse?
Well, if the wind direction reverses, then we could, the wake would meander, but then such a reversal would be, it would be catastrophic in one sense. But what is important is that while we are modeling, we ensure that we are capturing a sufficient amount of the effect, if you can remember from our vortex lattice, each of those filaments what becomes a decision point, or the engineering that comes into this, is how much of that wake does affect based on distances and conditions. And that is what kind of affects also the velocity patterns that it might generate. So I would kind of make it even, I would take that question and then make it even more, I would say, broader, is that yes, I mean, it's not just about reversal, it's just about how much. And that in practical terms, it also comes down to, we could actually, in mathematically and even computationally, we could get the results from a lattice which is infinitely far. But then that is where we need to think that whether we should be considering that, whether it actually does even make physically significant contributions based on what we are considering or not as well. So
all right,
very
is Lake Superior a good area to use wind turbines?
Depending on which part of Lake Superior. Yeah. So I would say that, sometimes this discussion applies not only to Lake Superior, also applies to, the coast of New England, So I have to tell you the truth, I am a wind power man, obviously. I dedicated my life, to wind power, but I try to have a really kind of a reasonable, approach to this. If you have a coastal area that is suitable for usage for other purposes, I don't know, tourism, human development, fisheries, etc. It's a navigational, important navigational artery, if you want, it's not good to put that wind farm. It's not really the right thing to do.
So don't put them where you need to navigate.
Exactly. Or where you need to fish, or you need to, I don't know, recreate, if you want, because that's
no,
the economy.
Don't mess up your sailing place, right?
That's true. That's true. Can create tourbillon emotions that make us lose the race.
Like
one thing.
All right. So
is,
what should high school students study to prepare for studying at Michigan Tech if they want to earn a degree where they can work with wind energy? So what should they take? What should they take, and then what should they major in?
Physics, mathematics, and physics. And then I would say, if they have the opportunity to go into some topic related either with structural mechanics or fluid mechanics, even better.
I'd say more than studying, I would say if we develop an enjoyment about those concepts, I will be very honest. The reason that I am doing this, of course, I do love, I've always loved airplanes since a very young age. I think when I was 3 years old, my mom baked me a cake in the form of an airplane, because that was what I, demanded, I guess. But my high school physics teacher who inspired me, or was instrumental in me coming to this path. Because just liking something is one thing, but then the way physics and mathematics were introduced to me, and the way I'm not great at math. It's not that you need to ace all mathematics or physics tests and exams. It's not about acing those exams. I mean, if you work for them, you ace them, that's good. But I would say the more important part is enjoying those, because there is beauty in that, and that is going to help you in any journey. Whether you go, you may decide that you like mathematics and physics and you don't want to do wind turbines at all. There are so many other things that you can do as well.
And I add one thing, something that we struggle here at MIM and engineering in Michigan Tech is to create a connection between the practical aspect of what we study with the theoretical aspect of what we study. In our wind turbines, wind energy course, or computational fluid dynamics, etc., is trying to show examples. So how this, this fundamental notion of the physics and the mathematics involved can help, to advance the technological aspects of a certain discipline. That's crucial, because it makes that the mathematics makes sense. By the way, one of my first cakes was Neil Armstrong, riding, a cartoon, and she took Neil Armstrong from one of my toys, and said, "Where is my Neil Armstrong? It's no longer my plastic."
So funny.
She put it mounted on the.
All right,
cartoon.
we're gonna go slightly over because there's so many questions. So and if anybody wants to log off, because we're already at 7 o'clock, but I'm going to keep going for just maybe 5 more questions. So I think this is a good one from Stephen. Is more power generated with higher humidity, air. Speaking of physics.
Oh, well, very interesting. It's not humidity per se what can affect, even though the two things go together. It's the changes in density that are going to, ultimately affect the energy production substantially, by the way, no? Because it's not the question of the machine per se. It's just that the power density, let's say how many, watts you're going to have per square meter of intercepted area is going to be carried by any kind of wind flow is going to depend with the cube of the velocity, the characteristic velocity, but linearly with the density. So you change your density of 5%, and then you're going to lose 5% of the energy that you can capture,
So we want these turbines to be at sea level then.
Well, yes, but there is something that you could do in terms a bit, of corrections that you can make, especially depending on which is the regime of operation, So I try to put it very short, but if let's say that if the turbine is already beyond its rated, generated power, essentially of a rated speed, let's say it's rated for creating maximum, or it's rated power at 11.4 meters per second. I'm citing a real number here, the RE power that we have seen before, and then the wind is coming at, 14 meters per second. The machine is what is called in the jargon operating in power limiting mode. So essentially all, the pitch mechanisms or whatever control mechanisms they are trying to dissipate power, not to overcome, the maximum limit of power that the electrical generation, the mechanisms, etc., the drivetrain can process. So in that case, if you have a reduction on the density of the air, you can repitch in order to move up to squeeze as much power from the wind, with that size of rotor until you, boom, hits the limit of what the machine behind the rotor can process. So essentially there are ways that you can operate, there. But well, there is a limit as as in anything else.
Okay. All right. Wait.
Also can affect
more questions. We want more questions. Do you see one you want to answer, Apurva?
So I'll take this one, which is what is being done to improve energy storage, that is batteries, so that energy can be used when needed.
You want to answer it?
Oh, I can both answer it.
Yeah.
Okay. Yeah. So I think that, well, this is not part of the line of research that we follow because we mostly go into utility scale machines, which are these big monstrosities, of hundreds of meters in diameter, or dozens at least, of meters in diameter. So where essentially batteries don't play a role there because, well, it would be impossible to produce an accumulation, device that is big enough economically, to store the amounts of energy, at these levels. Nevertheless, essentially what I'm trying to do is some sort of balance, answer here. So in terms of isolated population with small aerogenerators, etc., what is called distributed power generation, batteries are very important, yes. But this, again, is not our field of expertise. We go to the big machines, which are the gross, of the energy.
Well, and the Husky Bytes audience, we've had, I think they're pretty savvy. They understand that we need power all the time. We need a base load, right?
I see a lot of beautiful questions that we're not going to have the time to answer all that.
Well, so why don't you put your own emails in the chat? Maybe Apurva, you can do that. And so if people want to follow up later, they can email you. I think that would be helpful. And I always like to give a closing remarks from each of you. So starting with Apurva and then closing off with you, Dr. Ponta. And from me, I want to thank everybody for your curiosity. And I think this was a great example of the kind of talk that you could spend a whole course or even career learning about. And so I thank you for both of you for taking the time out of your evenings to prepare the talk and to give it. I learned a lot as usual, and I just want to really thank you again. And so with that, some closing remarks from you, Apurva.
Thank you so much. This has been fun. Some of you might see me in local schools. I also, I'm part of engineering ambassadors. So we go to local schools and have one, I think it's generally their science or math class where we introduce one small concept, and it's always fun to talk to grade school kids. They're always extremely enthusiastic, and just to see their faces light up, I think that gives me a lot of joy. So I'm thank you for having us over here, and it's been great.
Yeah. So well, I would say, I was thinking about which kind of, closing remark. I would say that for all the people in the audience, that they are just trying to go into engineering, or thinking about that, so I think that the key is something that we discussed before, how to find the balance between what the science that is needed, in order to do good engineering and not losing track, essentially keeping your feet on the ground, so essentially, which are the objectives, of the exercise, if you want, or the application of science for a good engineer. In that balance, which is sometimes a line which is not so easy to, navigate, that's good, sail, you have to trim your sails in the right way, not too far away, not too close, to choke them, anyway. And in that exercise, something that Apurva said is fundamental, trying to associate the notions of science is a good exercise at the beginning with something that you love. We have something in common with Apurva. I love the history of aeronautics. I read that just for pleasure. Sometimes when I try to relax, I go into the aerodynamics of the F6X Hellcat. That's why the font is there. So things like that. So how they negotiated, in that era to create with no computers, no nothing. These magnificent machines. Anyway, so that would be my piece of advice for future engineers. Try to see, not rely only on the practical knowledge, not rely only on the super abstract science. Try to create the bridge between the two. Is the way that you're going to empower your way of doing engineering.
So both of you, your passion for your subject has come through this whole evening, and it's been a real pleasure to be with you. Thank you both. Thank you, audience. We'll see you next week. The topic is butterflies, moths, and other bugs. Fruit flies, butterflies, moths, and fruit flies in the Kiwana. So see you next week for our last Husky Bites of the year. Bye-bye.